Welcome to Math with Professor V. In this video, I'll be working through and solving the latest exam, Exam 3, that my Calculus 3 class took this summer. And this exam covered multiple integrals, so double, triple integrals, integrals in polar, cylindrical, spherical coordinate systems, the Jacobian, and lots more good stuff. So stay tuned if you want to review any of those topics. That's what I'll be doing right now. First question said, reverse the order of integration and then evaluate the integral. Be sure to include a 2D graph of the integration region. So the integration region is going to be in the xy plane based on the differentials that we see here. Let's graph that first before we go ahead and reverse the order of integration. So we're going to make it now dx and then dy. Which is a good idea because, I mean, how on earth would you find the antiderivative of 1 over y to the 4th plus 1 with respect to y? You would just cry. I don't think you would. Okay, so let's look at the limits that are currently given. I can see that x is going from 0 to 27, and then y starts at, that's a 3, cube root of x all the way up to 3. Okay, so this is all happening in the first quadrant. Let's get this labeled and ready to go. X-axis, y-axis. X goes from 0 to 27, perfect. Y goes from cube root of x to 3. So we have to be careful. Cube root of x is concave down in the first quadrant, and it will have 27, 3 as a point on its graph. Let me get that concavity happening. Beautiful. So that's y equals cube root of x. Now notice, y goes from cube root of x to 3, okay? So you have to identify the correct integration region. We have to be able to shade it correctly so that when we switch the limits, we don't get things messed up. Y is bounded below by cube root of x and bounded above by 3. Bounded below by cube root of x, bounded above by 3. So this is my integration region here, this upper portion, not the lower portion. Can you see that? If it had been this region, the limits for y would have been 0 to cube root of x. So that's important. Okay, now we're going to switch the order up. Yes, we are. So then that means the limits for y are going to be on the very outside. Those need to be constant. So y is bounded between 0 and 3. And then limits for x, well, let's see. Draw a little line segment in the x direction, okay? And you look from left to right, always in increasing direction. X gets bigger this way. Where it hits first is the lower bound. Where it hits second is the upper bound. So this is x equals 0. This is x equals y cubed. X equals 0 up until y cubed. Why am I saying y cubed? Well, this curve right here is y equals cube root of x, yes? But when I'm giving limits for x, I have to have isolated x in terms of y in this case. So y equals cube root of x is the same as x equals y cubed. Okay, so those are our new limits of integration. Let's set up our new integral, and then we do have to finish and evaluate it. So we'll have 0 to 3 outside, 0 to y cubed now, and then 1 over y to the 4th plus 1 dx dy. Beautiful. Well, this was the whole point of reversing the order of integration, because now taking antiderivative with respect to x, I don't see any x's, so this is just a constant. And then I'm totally fine. I told my students, you can do the shortcut and do some steps in your head. I'm just going to pick up an x, right, when I antidifferentiate with respect to x, and then evaluate it at upper limit minus lower limit. So I'm just going to slap a y cubed on the numerator, and that first step is done. So 0 to 3 y cubed over y to the 4th plus 1 dy. Now, if that was too many steps being skipped for you, then go back, watch one of the video lectures on iterated integrals, multiple integrals, because I'll go more in depth and give you a proper lecture, but the purpose of working through the exam in this video is just to kind of give you a good overview, and so my students can see how they did or where they might have made some mistakes. Okay, from here, what do we do in order to evaluate the remainder of the integral? We're just going to do a u sub. Notice the numerator is 1 degree lower than the denominator. Perfect. So I'm going to go ahead, let u equal y to the fourth plus 1. Then du is 4y cubed dy. So 1/4 du y cubed dy. And then we do need to change our limits of integration as well. So u of 0, substituting in, these are limits for y, so that's where they get plugged in. U of 0 would be 0 to the fourth plus 1. And then u of 3 would be 3 to the fourth plus 1, that's 82. Okay, so let's rewrite everything now in terms of u. We've got this 1/4 sitting outside. Integral 1 to 82, 1 over u du. Yes? Beautiful. Antiderivative of 1 over u, natural log absolute value of u, and this is going to get evaluated from 1 to 82. So then this is 1/4 natural log of 82 minus natural log of 1. Well, that's just 0. So final answer, we have 1/4 natural log 82. Good? Okay, that's it. As you'll notice, pretty much in every single problem, there's going to be graphing. There's going to be graphing. Okay, moving on, next question number 2. Change the Cartesian integral to an equivalent polar integral and then evaluate. Be sure to include a 2D graph of the integration region. So we're integrating over the xy plane, but we're going to change it so everything's in terms of r and theta. So first let's look at what's going on. What are the limits in terms of x and y telling us that the integration region is? How is it being bounded? So y is on the very outside. Y is bounded between 0 and natural log of 7. And then x is bounded between 0 and square root of natural log of 7 squared minus y squared. At this point in your calculus career, you should recognize that this equation represents the right half of a circle with radius natural log of 7. If you don't, I'll do a quick recap. We know standard form for equation of a circle centered at the origin at 0, 0 is x squared plus y squared equals r squared. If you solve for y, you get plus or minus square root r squared minus x squared, and in this case the positive radical is the upper half of the circle and the negative radical is the lower half of the circle. Similarly, if we solve for x, then you get plus or minus square root r squared minus y squared. The positive radical is the right half of the circle and the negative radical is the left half. And oh my goodness, you integrate over so many circles in Calc 3 that it's helpful just to put that to memory. It happens naturally, if we're being perfectly honest. Okay, so notice we only have the right half of the circle with radius ln of 7, and then y is bounded between 0 and ln of 7, so no negative y values. So actually we're, again, only in the first quadrant. So some students missed that. One boo-boo I saw was that they graphed the entire right half of the circle, which was not correct. ln of 7, that's the radius. So I'm just labeling it, but it's only this portion. This is the integration region. Okay, so now when we switch to polar coordinates, we want to figure out what the limits are in terms of theta and r. We're only in the first quadrant, so theta is bounded between 0 and pi over 2. And then limits for r. If you're having a difficult time figuring it out, here's the tip I give my students. Start at the origin and then draw a ray or little line segment going outwards. Where it hits is the upper limit on its way out, and then where it started from is the lower limit. So it started at the origin, it started at 0, and it ends at the circle. The circle's equation in polar is just r equals ln of 7, right? Everywhere it ends is ln of 7. So r goes from 0 to ln of 7. And then this is e raised to the x squared plus y squared. I know the exponent looks a little low, but I told them. So in polar coordinates, this would be e raised to the square root of r squared. We don't have to worry about keeping absolute value. R is going to be positive, so this is just e to the r. Good? Do you remember what dx dy becomes in polar? Yes, r dr d theta. So I think we're ready to go. Let's rewrite everything in terms of r and theta. So now we're going to have 0 to pi over 2, 0 to ln of 7. Integrand is e to the r times r dr d theta. Good. Now, there's no thetas anywhere. So just to simplify things, I'm going to multiply by pi over 2 minus 0 and get rid of the d theta. So this is just pi over 2, 0 to ln of 7, r times e to the r dr. And this time, no u sub is going to save us. We got to do integration by parts. So we're going to pick u and dv. We have to pick them appropriately. When you have a polynomial and an exponential function, the polynomial should be u because you want it to simplify or reduce degree as you keep differentiating. If you picked r to be dv, when you find v, then it becomes 1/2 r squared, which just makes things worse. So you want to lower that degree. So u is r, dv is e to the r dr, and then that means du is dr, and v is e to the r. Okay, so I'm going to rewrite everything. We have pi over 2 out here, and then our by parts formula tells us we have u times v outside the integral. So that's r e to the r. That already is going to get evaluated from 0 to ln of 7 minus integral 0 to ln of 7 of v times du, which in this case is e to the r dr. Good? Okay, then this is pi over 2. I'm going to wait to evaluate everything all together at the limits, so I'm just going to write this as r e to the r minus antiderivative of e to the r is just e to the r from 0 to ln of 7. And then now let's see, we've got pi over 2 times ln of 7 times e to the ln of 7 minus e to the ln of 7 minus 0 times e to the 0, that's 0, plus e to the 0 plus 1. And then e to the ln of 7 is 7. So basically I just have now pi over 2 times 7 ln of 7. Watch this. This is minus 7 plus 1, which is minus 6. And we're done. That's our final answer. A few people distributed the pi over 2, which was fine. I don't care. So they had, or they just distributed the 2. It doesn't matter. As long as they simplified their logarithms and everything correctly, we're good to go. Okay? All right, here we go. Next idea, surface area. So find the surface area of the part of the hyperbolic paraboloid, z equals y squared minus x squared, our beloved saddle, that lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. You must also include a 2D graph of the integration region. So I didn't need a graph of the solid. When you're finding surface area, the integration region is all that's necessary to determine the limits, right, on your integral. So that's all I needed a graph of. Now, remember, how do we find surface area? Well, it's double integral over some region D, and then we have ds. And depending on how our surface is defined, ds can change slightly. But notice here the surface, we're trying to find surface area of the hyperbolic paraboloid. So that's what we use to find ds. These cylinders, those tell me my base region, the portion of the surface whose area I'm finding. So that just tells me what my limits should be. I don't use these to find ds. Okay, so since my surface is a function of x and y, then in this particular case, ds is going to be defined to be square root z sub x, so partial derivative of z with respect to x squared, plus partial of z with respect to y squared plus 1 dA. Okay, dA could be dx dy, dy dx, r dr d theta, depending on how things turn out. So I'm just going to leave it general right now till we decide what coordinate system we want to use. So whatever you're finding surface area of, that's the function that you use to find ds. These guys here tell you which portion of this surface we're finding the area of, and they determine the limits of integration on this double integral. Okay, so that's all that I needed the graph of. X squared plus y squared equals 1, x squared plus y squared equals 4. Those are just two circles centered at the origin with radii 1 and 2 respectively. So boop, there's one circle. And then let me make this one bigger. Good. And then I'll just label, that's 1, that's 2. So here's the integration region. We're finding the surface area of the saddle, that hyperbolic paraboloid, that lives above this lovely donut. Okay? Good. I'm feeling like we're going to go polar, you know, but let's just wait and see. So let's go ahead and start computing ds. Partial with respect to x would be negative 2x quantity squared. Partial with respect to y, positive 2y quantity squared plus 1 dA. Oh yeah, I'm definitely seeing this as a polar situation because this is square root 4x squared plus 4y squared plus 1 dA. Should we tell the people we're going to go polar? Okay, then I'll ditch this equal sign. We'll do it in the next line. We don't want anyone in the dark. And then this is rad for r squared plus 1, and dA will be r dr d theta. And then yes, my limits of integration for theta are going to go from 0 to 2 pi all the way around. So 0 to 2 pi. And then limits for r, in this case, are 1 to 2. So start at the origin, draw a ray outward. Where it hits first is the lower limit, second is the upper limit. 1 to 2. Okay, here we go. So surface area, or sometimes you can write area of the surface. I see that done too, or I've done it. 0 to 2 pi, 1 to 2, and then you're just integrating ds. So this is rad 4r squared plus 1 r dr d theta. Again, all the limits are constant. There's nothing's a function of theta, so I'm just going to get rid of d theta, 0 to 2 pi, and just slap a 2 pi on the front. And then we have 1 to 2 r times, this is 4r squared plus 1 to the 1/2 dr. Okay, and then I'm just going to do the u sub in my head. So we have 2 pi. You know, if you want to write it out, that's fine. You would let all of this be u, and then du would be 8r dr. So I'm going to pick up a 1/8 when I integrate. Also, the new exponent here is going to be 3/2, and we always divide by the new exponent when we integrate, so I'm going to also have a 2/3 out front. And then this all gets evaluated from 1 to 2. Since I didn't actually ever do the u sub, I keep these limits. Okay, so let's see what happens now. This 4 cancels with the 8, so there's a 2 now in the denominator. That's pi over 6 times 4 times 2 squared is 4 plus 1 to the 3/2 minus 4 plus 1, that's 5 to the 3/2. So that's 17 to the 3/2 minus 5 to the 3/2. I was fine if they left it like that. That's 100% for me, not a problem. The back of the book though, because this came straight out of their homework, wrote it, which some of them did too, which is cool, 17 rad 17 minus 5 rad 5. Same thing, either one we love. Okay, that was it. How are we doing? Okay, next one is perhaps one of the spiciest problems on the test. I don't know if the picture showed up well here. Oh, it actually did. Okay, solve the problem. Be sure to include a 2D graph of the base region as part of your work. You should have 3 2D graphs total. So the figure shows the region of integration for the integral, 0 to 1, rad x to 1, 0 to 1 minus y, f of x, y, z, dz, dy, dx. Rewrite this integral as an equivalent iterated integral in the 5 other orders. Okay, so they just had to set it up. Obviously, they weren't given what this function f was, so they couldn't evaluate it. I just wanted to see if they could rewrite the order of integration and understand geometrically what's going on. So let's do the first reordering in the xy plane. So I'll keep dz here, and I'm just going to switch the outer two, and that should be the easiest one. Here we go. So they needed 3 2D graphs, meaning one of the xy plane used as the base, one of the yz plane used as the base, and lastly the xz plane used as the base. So here we go. If we're going to do the xy plane as the base, hopefully you can see here, the limits for x in this given integral, the first one, go from 0 to 1, and then y goes from square root of x to 1. So let's get that graphed before we try to flip it. So x goes from 0 to 1, y goes from rad x to 1, rad x to 1. Okay. So that means rad x is the lower bound on y and the upper bound is 1. So it's this portion. Boop, boop, boop. Now, if we're going to switch it the other way, then we want limits for y on the outside. Those need to be constant. So y is still going from 0 to 1. Now, what about x? X goes from 0 to this curve, which is y equals rad x, but if I solve for x as a function of y, it's x equals y squared. So x is going to go from 0 to y squared. Since I'm only switching the outer two differentials, the order of the last two variables, then I don't have to worry about changing the limits for z because it stayed put. So the height of the region is still going to be the same. It goes from 0 up until the plane, z equals 1 minus y. It's bounded in the same way. So this first reordering, we're going to have 0 to 1, 0 to y squared, 0 to 1 minus y, that doesn't change, and then f dz dx dy. Good? Okay, beautiful. Let me get rid of this so we have some room. Okay, now let's go ahead. Let's use the yz plane as the base. So if you look at the yz plane, hopefully you can see we just have a triangular base region that we're integrating over, namely z equals 1 minus y. So let's go ahead and graph that. Y, c, 1, 1. So z equals 1 minus y is a plane in 3 space, but in 2 space, yes, it's a line. So this is the base region. Okay. So let's see. If we have limits for y on the outside, y is bounded between 0 and 1, then z is bounded from 0 up until this line here, which is z equals 1 minus y. So z would go 0 to 1 minus y. And then what about x? So this is where it's a little tricky. Now you got to look at the 3D graph and look in increasing direction for x. So x increases this way. X increases this way. Yes? Okay. So notice what's bounding the solid below in the x direction. It's just the yz plane here. So that's just going to be x equals 0. And then what bounds the solid in the x direction above? It's this surface right here, y equals rad x. But if I'm giving limits for x, I have to solve for x in terms of y. So this would be x equals y squared. Also imagine you're sending some projectile through the solid. Where does it hit first? It hits first right here, which is at x equals 0. And where does it exit? It exits through the surface, y equals rad x, which is x equals y squared. Okay, so limits for x are going to go from 0 to y squared. Good, so let's set it up now. Since I have my limits for y as constant, then dy is on the very, very outside. So 0 to 1, 0 to 1 minus y, 0 to y squared, f, dx, dz, dy. And then if I want to switch it, it's not too bad. So if I'm going to switch it, let's keep dx. We're going to go dy dz instead, okay? So it's still 0 to y squared. This is going to switch now. So look at the base region. Just look at the base region. Z's limits have to be constant. Z is still bounded between 0 and 1. Now limits for y, look at the base region. In the y direction, we're coming this way. Bounded below by y equals 0. Bounded above by the line. What's the line's equation? Not z equals 1 minus y. I'm giving limits for y. So it's y equals 1 minus z. So you just go 0 to 1 minus z. Good? Okay. Last ordering is perhaps the trickiest. That's using the xz plane as the base. So, what's the base region look like in the xz plane? Look over here. Let me erase this so it's not too messy. So in the xz plane, we basically have the intersection of this surface, y equals rad x, and this plane here, 1 minus y, projected back here, okay, over the xz plane. So what I want to do is I can basically substitute and find this intersection and how it appears in the xz plane. I'm just going to substitute in for y rad x right here. So z equals 1 minus rad x is going to give me the intersection of this curve here, and then projecting that into the xz plane where y is 0, we're going to have that base region for our integral. Okay, so do you remember the equation? It was z equals 1 minus rad x. So it's going to look like so. Okay, 1 minus rad x. Do you remember rad x looks like this? 1 minus rad x, well, putting a negative, let me just add a page if you'll allow me. Will you allow it? Okay, good. Minus rad x means flip it, and then plus 1 means shift it up 1. So it looks something like that. A few students, you know what they did? They got the concavity wrong. Yes, so it cost them a little bit. So here's 1 minus rad x curves downward like that, okay? Z equals 1 minus rad x, and then this is the region. This is the base region. Okay, very good. So say we have limits for x on the very outside. Those are going to be my constant limits, 0 to 1. Z would go from 0 to 1 minus rad x, and then now we need to look back at the 3D solid, figure out what are the limits for y. Okay, again, I say, imagine something projectile being shot through the solid in the y direction, in increasing y direction. Where does it enter first? Where does it exit? So projectile coming in hot this way, this way. What does it hit first? This surface. But remember, I'm giving limits for y. Okay, so I can say y equals rad x. Perfect. Where does it exit? It exits through this surface. But I'm not going to say 1 minus y. No. I'm going to solve and say it exits through y equals 1 minus z. Okay, let me show that for you again. Shall I draw the projectile coming through? Woo! Here it is. It enters here at y equals rad x, and it exits through here, y equals 1 minus z. You can draw it and see it in any direction. Enter, exit. Okay? Very good. So rad x to 1 minus z. Those are my limits for y. Rad x to 1 minus z. So we can set it up now. 0 to 1, 0 to 1 minus rad x to 1 minus z, f, dy dz dx. And then lastly, if I'm going to switch it around, I'm just going to switch the outer two, x and z. Okay. So this is going to stay rad x 1 minus z f dy dx dz. So limits for z now need to be constant. Z is bounded between 0 and 1. Next, I need limits for x. So from left to right, what's bounding x on the left? That's, yes, very good. X equals 0. And then on the right, it's the curve. It's the curve z equals 1 minus rad x, but I have to solve for x in terms of z. So rad x equals 1 minus z, which means x is 1 minus z quantity squared. So that's going to be the upper limit right here. 1 minus z quantity squared. Yes, so much going on. Can I tell you something amazing though? They did so well. Almost everyone got this perfectly right. They did great. Yep. Okay, that's it for question number 4. Moving on. Question number 5. Set up only the iterated integral for evaluating triple integral of f r dz dr d theta or dz r dr d theta, whatever. It's telling us we're in cylindrical, people, over the given region E. You must include a 2D graph of the base region, so just over the xy plane or using r and theta. 3D graph is optional. So E is the rectangular solid whose base is the triangle. So this is what we need the graph of. Triangle that has vertices at 0, 0, 0, 10, and 10, 10. And then whose top lies in the plane z equals 7. You know, a lot of them did still give me a 3D graph. So maybe I'll make one for you. So let's first draw the base region. 10, 10. It's a triangle. Vertices at 0, 0, 0, 10, and 10, 10. So this is the base of my solid E. Okay. Shade it in. And then based on the directions of the problem, I can tell we're going to be using cylindrical coordinates. So I have to figure out the limits for this region in terms of r and theta. Okay. So theta, let's see. Remember, we start here, positive x-axis, that's theta equals 0. There's nothing. The solid's base doesn't exist until I hit right here. Well, what is this? Since this is at 10, 10, I know this is a line, slope 1. That makes 45 degree or pi over 4 angle with the positive x-axis. So the base starts when theta is pi over 4, and it continues up until right here, positive y-axis, which is at pi over 2. Those are our limits for theta. Are we good? Excellent. Now what about r? R is a little more spicy. So r, you can still do the same trick. Start at the origin, draw a line going outward. This is the lower limit, 0. Upper limit, right here, this horizontal line. 0 to the horizontal line. So 0 to the horizontal line. What's the horizontal line's equation? Y equals 10. But I can't write that. We're in polar. We're in polar, people. Well, y in polar is r sine theta. I need a limit for r, so I got to isolate r. So r is 10 over sine theta, which, yes, you must simplify to 10 cosecant theta, since we're going to be integrating. So r goes from 0 to 10 cosecant theta. Good. And then lastly, I need limits for z. And they told me the base is this triangle. Okay, well, if we're in the xy plane, then that means we're starting where z is 0. And then the top is the plane z equals 7. So we're going up to 7. Okay, so we're ready. So theta goes pi over 4 to pi over 2. R goes 0 to 10 cosecant theta. Z goes 0 to 7. We have a function f. Notice. Yes, we have a function. So this integral doesn't represent a volume. We're evaluating a triple integral, right, over some solid region, but we're integrating a function over that. It's some 4-dimensional quantity. It's not a volume. And then you have f, r, dz, dr, d theta. So that's all I needed. I needed this 2D graph, and then I needed that integral. And then some of them did give me a little 3D moment. So let's do it. Why not? Y, X, Z. So here's 10, here's 10, and then it's the portion up here. Yes, yes, Professor V. Good. Boom. Okay, and then upper bound is where Z equals 7. That's the height. One more. Beautiful. Wow, wow, wow. As much as I appreciate how technology helps with the graphing, I have to say, and we were discussing this in my class, sometimes I graph better with paper because the grip, and I can do more shading and whatnot. But anyways, so here's the solid. Do we love it? Oh, I should do yellow to stay on theme. Okay, let's not get carried away. Actually, I hate that yellow. Abort mission. You get the idea. Okay, very good. Halfway through. Use a spherical coordinate integral to find the volume of the given solid. You must include a 3D labeled graph of the solid. So just a 3D graph. Usually in spherical, the 2Ds aren't so helpful, you know. So it's the solid bounded below by the sphere. Rho equals 2 cosine phi, and above by the cone, z equals rad x squared plus y squared. Okay. So yeah, this looks funky. This is rho equals 2 cosine phi. I know most Americans say phi. I'm sorry, all I ever heard was phi because when I went to university, my professors were not Americans. So that's how I always said it. And then finally I heard my students and other professors, they say phi, and it's just been so ingrained to say phi. So if that's strange to you, I'm sorry. That's how they say it in Greek though. Anyways, so let's see. We have the sphere bounding the solid below, and then it's bounded above by this cone here. Why don't we go ahead, find the intersection? Yes, I already can tell, and I emphasize to my class, this is a sphere, when you see these equations in spherical, centered on the z-axis. So the center is at 0, 0, 1, and the radius of that sphere is also 1. This is always 2 times the radius. That's something we derived it once together, and then I said, just put it to memory. It comes up so often. But if you didn't know that, let me show you what to do. So multiply both sides by rho, then you get rho squared is 2 rho cosine phi, and then go back to rectangular. So rho squared is x squared plus y squared plus z squared equals 2z. Good? Okay, so this is the sphere's equation. And then from here, if you were to complete the square, you have x squared plus y squared plus z squared minus 2z, and then I'd put plus 1, right, to complete the square. So x squared plus y squared plus z minus 1 quantity squared is 1. So that's where you could see, center's at 0, 0, 1, radius is 1. Now what I'm interested in is where does this beloved sphere intersect the cone that was given? And maybe you can already tell. Maybe you're a sharp little cookie. But if not, all you could do is just say, all right, z squared is equal to x squared plus y squared, right? And I'm just going to replace x squared plus y squared right here with z squared to find the intersection. So then I have z squared plus z squared is 2z. So 2z squared is 2z, z squared is z. No, we don't divide by z's. You can only do that with r's and rho's, okay? But in this case, z squared minus z is 0. Factor out a z. And I can see the sphere and the cone are going to intersect when z is 0 and when z is 1. That makes perfect sense. So let's draw this 3D graph, and then we can get the ball rolling on setting up the integral. So sphere is sitting on top of the xy plane. That's important. It's not centered at the origin. So you got to go up to 2 like so. Okay. Let's see. Not bad. We'll take it. Here's the sphere. It intersects the cone when z is 0, okay? And then again when z is 1. So that's going to be right here. That's where the cone intersects the sphere. That needs to be precise. Then, and the cone's coming all the way around, shade the solid correctly. The solid is bounded below by the sphere. So the solid's above the sphere. The sphere is the lower bound. And then it's bounded above by the cone. So the region that we're after is here, here, all the way around as well. Okay? All the way around. So that's helpful. So my limits for theta are going to go 0 to 2 pi. My limits for phi, or phi, whatever you like to say. So we measure phi starting from the positive z-axis all the way down to pi. That's the biggest it can be. Starting here, when phi is 0, no solid, no solid, no solid. Starts right here at the cone. The cone's equation is phi equals pi over 4. I've shown that before, how to derive it. Basically, it's that z is equal to r, and then if you draw your triangle, that happens at pi over 4. This is a common cone that comes up all the time, so I figured they memorized that, and we've talked about that. That's fine to do. So this is pi over 4. They're still solid. They're still solid. Now there's no more solid. It ends right here when phi is pi over 2. Don't go past that. Don't go past that. There's nothing over here. Okay? And then rho's limits, rho you can kind of treat the way we do r's limits as well. So you start at the origin, go outward. Where it hits is the upper bound on its way out. So from the origin, what does it hit? The sphere. Origin to sphere. Origin to sphere. The cone is not involved in the bounds for rho. The cone basically just stops the angle phi, but it's not involved, can you see, with how we determine rho. Rho is solely determined by the sphere. Well, what was the sphere's equation? 2 cosine phi, correct. So rho is going to go from 0 to 2 cosine phi. Good? Okay. So this time, yes, we're finding a volume. So we're just going to do triple integral over this solid. Did they give it a name? No. I'll call it E. dv. We're in spherical. So this is going to go 0 to 2 pi, pi over 4 to pi over 2. Rho goes to 0 to cosine phi. And then remember, dv is rho squared sine phi d rho d phi d theta. Okay, nothing is a function of theta, so I can go ahead, just slap a 2 pi on here. Then we have pi over 4 to pi over 2. I can't break up this integral because notice all the limits are not constant. This is a function of phi, so we got to keep it as is. Sorry, guys. Okay. So let me keep writing out 0 to cosine phi. And then we have rho squared sine phi d rho d phi. Okay, I need another page again. Don't worry about my class. They get the exam photocopied single-sided. Okay, so I'm going to integrate with respect to rho first. It's going to become rho cubed over 3, and I'm going to plug in the limits while I'm at it. Over 3, I'm going to put outside. So 2 pi over 3, we're going to go pi over 4 to pi over 2, and then it's 2 cosine phi cubed sine phi d phi. Good? Okay, this is 8. Let's take it outside. Take it outside, people. So 8 times 2 pi, 16 pi over 3, pi over 4, pi over 2, cosine cube phi, sine phi d phi. Okay, and then here, not bad. We're just going to do a little u sub because we've got this odd man out. So I'm going to do it in my head. If u is cosine phi, du is negative sine phi d phi. And then it's going to be cosine to the 4th over 4, right? So negative 16 pi over 3 times 1/4 cosine to the 4th phi from pi over 4 to pi over 2. And then this is going to be, here, let me put a bracket here. You can just clean up all the constants outside, right? This cancels. This is now 4. So negative 4 pi over 3. And then cosine pi over 2 to the 4th, that's 0, minus cosine of pi over 4 is 1 over rad 2 to the 4th. That's 1/4. So the negatives cancel. 4 pi over 3 times 1/4. Final answer is pi over 3. Good. Most of them did very well. Some of them got the integral correct, but their drawing was not correct, so they lost points for that. Okay, next. Use the given transformation to evaluate the integral. No graphs required. I gave them such an easy Jacobian problem because they learned it only 2 days before the exam. That's the peril of summer school. Everything's so fast-paced. So anyways, the transformations given, it ended up being super straightforward, and I told them no graph is required. And normally, problems using the Jacobian are a lot more involved and beautiful, but I took pity on their poor souls. Okay, so x is 2u, y is 5v, z is 4w. We have triple integral over r. All that stuff raised to the pi, dx, dy, dz, and r is the interior of this ellipsoid that's given. So let's see what this region becomes if I apply the given transformation. So I'm going to substitute in 2u for x, so 2u squared over 4 plus 5v squared over 25 plus 4w squared over 16 equals 1. And then I can see, oh, how lovely. Everything, all the constants cancel. I just have u squared plus v squared plus w squared is 1. So in the UVW plane, this is a sphere with radius 1. Okay, now I'm inclined to do yet another transformation, and that would be to switch to the spherical coordinate system, okay? So we're going to go from XYZ to UVW to spherical. So rho, theta, phi. Okay, so going from XYZ to UVW, we got to figure out what the Jacobian is. We know what the Jacobian is going to spherical. It's rho squared sine phi. But we have another Jacobian because we applied this transformation here. So how do I compute it? You take del XYZ, del UVW, and I mean, things are as clean as can be. Partial derivative of x with respect to u is just 2. Partial of x with respect to v and w are 0. Similarly, partial of y with respect to u is 0. Partial of y with respect to v is 5, and then 0. And the last row is 0, 0, 4. When you have a fully diagonalized matrix and you're taking the determinant, you just take the product along the diagonal. And this is 40. So there's our Jacobian. Okay, so we're going from this region R. I'm going to call this my new region S. Okay, and rewrite the integral accordingly. So we have triple integral over S. This whole quantity is u squared plus v squared plus w squared to the pi. And then we have du 40 times du dv dw in some order. So I'll just put dv. But then from here, we discussed we're going to want to go to spherical coordinates next. So I can integrate over this region, this solid, which is a sphere with radius 1. So now I'm going to replace u squared v squared w squared with rho squared to the pi. I still have this 40, and then dv is rho squared sine phi d rho d phi d theta. Now, what are the limits? We have a sphere radius 1, the whole entire sphere. So theta goes 0 to 2 pi, phi goes 0 to pi, rho goes 0 to 1. Boom. One thing some students forgot, I think they just got a little happy-go-lucky, they forgot all about the Jacobian. That was a big problem. But they set everything else up fine. They just forgot to do this entirely. So you can't just change from one coordinate system to another and not factor in that there's going to be a change to that differential. All right, the rest of the integral falls into place nicely because look at all the limits are constant, so we can just break everybody up. In fact, I'm going to slap a 2 pi on the outside and take the 40 out. So this is going to be gone. And now we've got 80 pi sitting out there. Look at us, aren't we fancy? And then 0 to pi, those are limits for phi. So I'm just going to put sine phi d phi. That part's done. And then 0 to 1 are the limits for rho. Now be careful. This is rho to the 2 pi times rho squared. So that's going to be rho to the 2 pi plus 2. And then we have d rho. Good? Okay, very nice. So then this is 80 pi times antiderivative of sine phi is negative cosine phi. But you know what I did? I didn't put a negative. I put the pi down here and the 0 here. And then antiderivative of rho to the 2 pi plus 2, you're going to add 1 to the exponent, divide by the new exponent out there, yep, and evaluate from 0 to 1. Okay. Then let's see here. This is going to be cosine of 0 minus cosine of 0 is 1 minus cosine of pi is negative 1. So this is just 2. And then this is going to be 1 to the 2 pi plus 3 minus 0 to the 2 pi plus 3. So this is just 1 minus 0. So we have 80 pi over 2 pi plus 3 times 2 times 1. So final answer is going to be 160 pi over 2 pi plus 3. No graph necessary, but if they wanted to draw me a sphere or an ellipsoid, it was welcomed. I don't think anyone did. Okay, almost there. Solve the following problem. Let D be the region that is bounded below by the cone phi equals pi over 4 and above by the sphere rho equals 6. Set up the triple integral for the volume of D in spherical coordinates. You must include a labeled sketch of the solid. So this time the cone is bounding the region from the bottom. It's bounded below by the cone, above by the sphere. Sphere's radius is 6. So this is basically going to look like a ice cream cone. Oh yeah. And then the cone makes an angle of pi over 4 with the positive z-axis, so something like that. So bounded below by the cone, so the cone's the lower bound. And then it's bounded above by the sphere, so the sphere is the upper bound. Okay, and they're just setting up in spherical coordinates. Okay, so theta, we're going all the way around. So 0 to 2 pi. What about phi? So phi starts at the positive z-axis, 0. It's there. They're solid. It stops right here at the cone. It stops at pi over 4. So 0 to pi over 4. And then what about rho? Starts at the origin, stops at the sphere. Starts at the origin, stops at the sphere. Does not involve the cone. The cone just determines when phi stops. So it goes 0 to sphere's equation, which is 6. This one actually would have been easy to evaluate. But you know what? They've done enough. So 0 to 2 pi, 0 to pi over 4, 0 to 6, and then this is going to be rho squared sine phi d rho d phi d theta. Boom. They did great. Maybe some of the graphs were not correct, but otherwise it was good. Okay. We're almost at the end, guys. Here we go. Number 9. Set up a triple integral. To find the volume of the indicated region, you must include a labeled sketch of the integration region 2D and 3D. Do not evaluate the integral. So it's the region bounded below by the xy plane. laterally by the cylinder r equals 2 cosine theta, and above by the plane z equals 7. So first let's draw the 2D graph of the base region, which since we're bounded below by the xy plane, then in the xy plane this is going to be my base region, r equals 2 cosine theta. We know that's a circle centered on the x-axis with radius 1. That's something, hopefully at this point, like all my students know that because we've done so many of these polar circles. So it's centered at 1, 0, and the radius is 1. Okay, there's the circle. This is the base region. So I'm going to use cylindrical coordinates. It didn't say what coordinate system to use. I don't think anyone tried spherical. Okay, so cylindrical is going to be the nicest here. Limits for theta. Theta goes from negative y-axis to positive y-axis. So it's going to be from negative pi over 2 to pi over 2. Okay. Limits for r. Again, start at the origin, go out. Start at the origin, go out. R starts at 0. It ends at the circle. The circle's equation is 2 cosine theta. Okay, so this is the base of the region. Z equals 0, this is the base. And then the top is the plane z equals 7. So I feel like we know it's going to go 0 to 7. Let's draw it though nicely, and then we'll set up our triple integral, and we're doing this in cylindrical. Okay, so we need this circle, this cute little circle in the xy plane. There's z, there's x, there's y. 1, 2. Okay. There. And then we're going to go up to 7. That's the height. Okay. Let me do a couple more so I have places to put them. You want them, if you're doing this like by hand, you know, you want them to be about the same height. That, well, not about, as close as possible to the exact same height. Okay, hopefully this looks decent. No, it's looking terrible. You guys, send me back to Art 101. Okay, it's a little too slanted. I'm just gonna just shade it in so we can blur our eyes. Okay, there we go. Beautiful. Should we add a little bit of dimension? That's enough. Let's not get carried away. Okay, flat top, there we go. So here we go, write out the integral. Theta goes negative pi over 2 to pi over 2. R goes 0 to 2 cosine theta. Z goes 0 to 7. So this should be R dz dr d theta. Okay, one more. We are at the home stretch. Beautiful. Last one says solve the problem. So evaluate the following triple integral by transforming to cylindrical or spherical coordinates. You must include a labeled graph of the integration region. So what is the integration region? It is this 3D, because this is a triple integral. We're integrating over the XYZ coordinate system. Yeah, okay. So let's identify what's going on. In the XY plane, I told them the 2D graph was optional, because maybe it's just so common sense, but for sure they needed the 3D graph in there. That's what the region is. In the XY plane, we've got a circle, because X goes all the way from negative 7 to 7. Y goes from top of circle, bottom circle. So we've got the whole circle, radius 7, centered at the origin. That's not bad. So here's X, here's Y, boom. Now, what about in the Z direction? So Z is bounded below by rad x squared plus y squared. That's a cone. and then bounded above by z equals 7. That's a plane. So can you imagine what that's looking like? I think so. I think you can. So here we go. X, Y, Z. Here's the plane z equals 7, 7, 7. Boom. Here's my cone. You know what? That came out too far. Let's just control ourselves a little bit better. There. Okay. Boop, 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 boop. So this base region right here, you can see the projection of the top of the cone, or that's really the plane z equals 7, right? That's bounding the integration region above, but that projection over the xy plane makes that circle that we drew. And then the cone is the lower bound. All of this is the lower bound here. So it goes from the cone to the plane. This is the graph that was needed. Some of them got confused. They drew something else. I don't know why. Okay, this is 7, excuse me. We need to label, always label. Labeled. So I'm going to go cylindrical. We can talk about what it would be if you went spherical. A couple people did it. I think only one did it successfully. So if you set this up in cylindrical, limits for theta are going to go 0 to 2 pi. Limits for r, 0 to 7. Hopefully that's clear, right? 0, 7, 0, 7. And then limits for z are, well, look, from the cone to the plane z equals 7. The cone's equation in cylindrical is z equals rad r squared, which is z equals r to 7. Okay, so yeah, if we set it up, then we have 0 to 2 pi, 0 to 7, r to 7, r dz dr d theta. Again, there's no theta, so I'm just going to do 2 pi, 0 to 7. There's no z, so I would just pick up a z and have 7 minus r times r, which is 7r minus r squared dr. And then that's 2 pi times 7 halves r squared minus 1/3 r cubed from 0 to 7. And then I noticed if I plug in 7, this is 7 cubed. This is also 7 cubed. So I can factor out 7 cubed. 2 pi times 7 cubed times 1/2 minus 1/3, which is 1/6. 1/6, oh shoot, this is all 1/6. Times 2 pi is going to be pi over 6. And 7 cubed is 343. I know that because that's one of my favorite cubes there is. So this is 343 pi over 3, which doesn't reduce, even though you feel like it should, right? Isn't that weird? 7 cubed being 343 has got to be one of the most beautiful things ever. Let me just take a moment to explain to you why. 7 cubed, 343. It makes a 7 sandwich. Do you see this? 7, 7. It's just such a lovely little sandwich. The way it looks too, I don't know. I don't have any tattoos, but I like it. I think it's silly to get it tattooed, but anyways, I digress. That's the answer. If you wanted to set it up in spherical, I'm not going to work through it, but we can talk about what the limits would be. Okay. So limits for theta, 0 to 2 pi. Limits for phi, let's see, starts at 0, stops at the cone, correct. The cone is at pi over 4. And then what about rho? So rho starts where? Rho starts at the origin, stops at the plane, z equals 7. Do you see that? Rho's going this way. So we got to go 0 to the plane, z equals 7. Well, what is z in spherical coordinates? Rho cosine phi equals 7. Solve for rho. 7 over cosine phi. So you should write 7 secant phi. So if you did it in spherical, these would be the limits. And then, you know, dv would just be different. You'd have rho squared sine phi, d rho d phi d theta. But the answer comes out the same. So that's that. There were 2 extra credit, but I feel like this video is long enough and I do have to get going. Oh my goodness. I'm gonna lift weights and then go to hot yoga and then go teach. So that ends the video now. But there were 2 extra credits. If you're interested in seeing them, let me know and I can make like a little bonus episode. I would say the first extra credit, a lot of people attempted, but they didn't get it right because the picture wasn't correctly labeled or the limits weren't right too, let's be honest. But anyways, hopefully you enjoyed the video. This is one of the most challenging parts of Calculus 3, but you know, with enough practice, you can get it down. Graphing is so essential though. Oh my God, you have to graph and you have to graph well. It's just one of those things. Okay, that's it. Give the video a thumbs up. Comment down below, what was your favorite question on the test? And some people were saying they liked the darker background, so I tried. I'm not as comfortable switching colors with it, but hopefully if you guys liked it better, let me know so I can keep it up. And also follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you guys so much. I'll be back sooner than later, although I am quite the busy bee these days. All right,